Good afternoon, everyone. It is really an honor to have you all here for the first seminar of the year. Today we have the pleasure to welcome Professor Lourdes Vega. She is a full professor in chemical engineering at the Khalifa University in Abu Dhabi. She acts as senior director of the Petroleum Institute, devoted to sustainable fuels from a broad perspective, and director and founder of the Research and Innovation Center on CO2 and Hydrogen, the REACH Center, that is focused on decarbonization, hydrogen, and clean energy. Professor Vega is an internationally recognized expert in molecular thermodynamics, clean energy, and sustainable products. Her research is focused on CO2 capture and utilization, hydrogen production, storage, transportation, and utilization. She is the recipient of several international awards, and she is listed as top 2% most cited worldwide scientist in chemical engineering. And one of her passions is to mentor young females to develop their full potential. So once again, welcome, Professor Vega. Thank you so much for accepting our invitation, and please feel free to start your presentation.
Thank you. Thank you. Thank you very much for the presentation. It is my real pleasure to be here today. Eu gosto muito. Very different to be here than to be online, like in the other seminar that I gave. This is much more alive. So thanks for the people attending virtually. But if you have the opportunity to come in person, this is much better. You see the young people in front of you expecting something. So I have to decide what to talk about today. And I have Fred insisting in giving a title. I don't give a title until I know what I'm going to talk about, which means I have to have my seminar ready. So it was like a fish eating its own tail, correct? But anyway, I gave you a title, so that's what I'm going to talk about today. So the title is Planet in Search for Sustainable Energy. That's the first part of the talk. And the second one is, what is the role of photocatalysis in achieving this goal? So it goes from a very, very general problem to a very specific details on something we can do for it. So that's like having a grain of sand in the whole beach, correct? Or a drop of water in the ocean. But water by drop, we have a whole ocean. And grain by grain, we have a beautiful beach, correct? So let's talk about this. First, I'm going to tell you where I'm coming from. I guess you know very well what I'm marking here. That's Rio in Brazil, o melhor país do mundo. And then here is another very nice country, which is the United Arab Emirates. So the United Arab Emirates is very close to Saudi Arabia in the same peninsula, but of course it's a different country. And contrary to what you can think, it's a country with a lot of water. So it's a desert, of course, you all know that. By the way, people are asking me about the weather. It's raining today like crazy, okay? Anyway, so, and then here we have Abu Dhabi, which is the capital of the country. Some people think it's Dubai. No, it's Abu Dhabi, which, by the way, has one of the largest reserves of oil in the world. 9% of the world oil is in Abu Dhabi. So these are some photos of beautiful Abu Dhabi. We have a little bit of everything. So we have the Louvre Museum. We have, of course, these large buildings. I actually live in this one. That from their perspective, it doesn't look the tallest, but it's the tallest. Then we have Formula One. We have this beautiful mosque. We have the turtles. We have camels. We have dessert. We have beautiful buildings, a little bit of everything. And then we have beautiful Khalifa University. So Khalifa University is a public research-intensive university that is located in Abu Dhabi, and it was founded in 2017, very young. But it's the fusion of 3 universities, the Petroleum Institute, Masdar Institute, and the old Khalifa University of Science, Technology, and Research. And it became public. Before it was private. As any university with big ambitions, one of the ambitions of the university is to be one of the best in the world. So we take care a lot about rankings, etc. And this is the last ranking. So we are ranked as 181 best university in the world by QS last year. That's a huge achievement, top 200%. And of course, because of that, we have to work very hard on research, publish in top journals, bring a lot of money, be the best on everything. So the pressure is on us. Anyway, so within that, we have several research centers, and one of them is the REACH Center. So REACH stands for Research and Innovation Center on CO2 and hydrogen. We cover other things, and of course, everyone knows what REACH means. No, but no. We are rich in knowledge, not rich in money yet, maybe. Okay, so this center was founded close after the university was founded, and the goal of the center is to work on efficient solutions for clean energy and sustainable fuels. And then in the center, we focus on the applications. We go from fundamental science to the applications, and then we focus on the applications for CCUS, hydrogen, and sustainable energies, and sustainable fuels. So we work on these three big pillars. We have divided ourselves into 5 themes. I will explain that later. This is to cover the specific projects, PhD, thesis, etc., that we have covering the different topics. The center was started with COVID. I don't know if you have realized, but we started in 2019. We started in Masdar. We were moved from Masdar to another building in the university, and then everything was closed because of COVID. So for 1.5 years, no labs, no nothing, people working at home, a lot of modeling, of course, review papers and a lot of modeling, and then we got ready to start with the labs that we started in 2021 again. So we try to combine both, as you will see later. We have more than 200 publications in 4 years, 12 patents. We expect to have more, a lot of presentations in conferences, and of course, as I say, we are not rich in money yet, but we need to raise money for research, so we also have external funding for our center. But what are we going to talk about today? So first, we are going to talk about climate change and greenhouse gases emissions. That's what I promised. Then we are going to talk about the technological avenues that we have to compensate, mitigate climate change. Then we will talk about decarbonization, hydrogen, and sustainable fuels as 3 of the things we can do in this direction, which is what we do at the REACH Center. And finally, we are going to talk about photocatalysis. So how many of you in the audience, not online, but in the audience, know about photocatalysis? Can you raise your hands? Okay, so I will ask the same question at the end of the seminar, and I really hope to see all the hands up. So please be with me until the end, okay? Very good. Okay, so well, I start, as is my professor hat, I start always with the definitions, correct? So what is climate change? Climate change is a significant and lasting change in the statistical distribution of the climate patterns that we have that include the atmospheres, the water, many things related to our planet that happens over periods of millions of years or few years. Both of them are referred as climate change. So the United Nations Framework Convention of Climate Change defines this as this change on the climate environment that are attributed directly or indirectly to the human activities that add in addition to the natural changes, okay? And then we have that in most of the cases when we talk about climate change, we don't talk about the changes for millions of years. We're actually talking about the changes that are attributed to the human activity that are called anthropogenic climate change. Why I'm explaining all this is because there are many people that are not believers. They think, the action of the humans is very small compared to millions of years. And this is true, but it's accelerating this climate change. And then we have something that is called global warming. So global warming is not the same as climate change, but is directly affected by climate change. And global warming responds to an unequivocal and continuous increase in the average of the temperature of the Earth associated to the climate. And here is a photo to show that. One image is better than 1,000 words. So this is the Earth in 1921. I don't have to explain the meaning of blue and red in any heat map, correct? So this is in 1921. This is the Earth last year, okay? And this is measured. So it's clear, It's clear that the Earth is warming up very rapidly, okay? Very impressive. So is climate change only an environmental problem? Because maybe we think, oh no, new generations, we care about the environment. I'm not a new generation, and I care about the environment. But anyway, it's not something that is in fashion, and we have to be green. Okay, so what are the consequences of this? Here you have some of the photos that you see when we talk about climate change. And then, of course, this is an environmental problem that affects people and planet, but it's not only an environmental problem. It's also an economical problem. In fact, this data is coming from a report. The data associated to disaster directly related to climate change in the US in 2018 is $160 billion. And now in a report from the UK, so the climate change could cost globally, the economy, as much as $23 trillion if we don't do anything. And if we only move from the energy we have right now to renewable energy, we can save $12 trillion. And why? Because if we have more disasters, then we have to put more money to recover from these disasters, correct? Okay, so what is the situation today? Today, unfortunately, is 2nd of May, because this data is updated every 5th of the month. So for Curitiba, maybe we have the data. But for today, we have the data from April. So this is a plot among many plots that you can use to follow the evolution of the concentration of CO2 into the atmosphere. So this is coming from Mauna Loa, and this is the CO2 concentration in ppms, and this is for a period of 5 years. So the red line is the monthly mean value centered in the middle of the month, and the black one is the same but corrected for the average season. So that is from 2007, where I started to follow up this. This was in the Boulder Conference on Thermodynamics, that the talk was given by Susan Solomon, who was the coordinator of the IPCC panel at that time. This is the data from yesterday, but it's actually from last month. So the trends are very similar. The numbers are not. So the data is last year at the same month, we have 421 almost. Now we have 425. I should tell you this is 3. This is more worrying for me than for you, because I have been following this for 17 years. And I update this every time I give a talk. And usually it was 2 ppms. Now, in the last 2 months, it's 3 ppms. ppm is very little, but in this, it's huge. So this is really to be worried. And that's what you see, no? In 2007, the average was 385, and now is 424. So it's a huge increase in few years. Furthermore, Susan Solomon explained to us, if we reach 400 ppms, that was 2007, there will be changes in the atmosphere, in the ambient, that will be irreversible. We hit that for the first time in 2019, and it has been continuously growing. So, of course, some of the changes will be difficult to recover, but we really have, there is an urgent need to stop some other things. But then you can tell me, but Professora, 5 years is nothing, correct? It's true. Now here you have the last 64 years, and we are all scientists. Do you see the slope? It's very, very steep. So then where are these things coming from? And now, from 1850 until 2022. So this is how it is changing since the Industrial Revolution. Okay? So where are these emissions coming from? Essentially from energy and power, from transportation, from industry, and from buildings. Okay? That's why the first part of my talk was a planet in search for sustainable energy. We will make it nicer. It's sustainable, secure, and affordable. Energy that we can always have, and energy we can pay. So this is called the trilemma in energy. It's not easy, and it's not a dilemma, it's a trilemma. Okay, so essentially what do we have to do? We have to change the trend of the curves and put it down. And this is why it's very difficult. So that's where we are right now. This is 2020. That's where we have to be. And what are these colors? These colors means predictions. Predictions can fail, of course, but predictions based on climate models that depend on what do we do. So here is no climate policies. Don't worry, we are not going to see that. If this happens, the planet will not survive. We cannot adapt that fast to this big change in temperature. neither the plants or the animals. And then we have the current policies. It's not enough. This is the Paris Agreement. So that's where we have to be. Okay, what can we do? That looks very depressing. No, no, no. You will know when we finish what is photocatalysis, but also some opportunities to help to change this, okay? So, well, I don't have to invent anything. I will use my favorite scientist, one of them, which is Einstein. And then he said, those who have the privilege to know have the duty to act. And we as scientists or as engineers have the duty to act from our side. We are not politicians. Politicians have their own rules. But as scientists, we can do it. We don't have to invent anything because everyone knows we just have to implement or find better ways of doing that. So here is a report by the energy system, by the International Energy Agency, in which it follows up how are we doing in the different clean energy processes. So here we have renewable energy efficiency, CCUS, hydrogen, digitalization, bioenergy, all of them. Okay, I'm not going to bother you with this. I'm going to make it short. So these are the same ones I put before, and then I want to use the traffic lights with the same meaning as a traffic light. So we can guess how many of them are green, yellow, or red. Any guess for how many are green? No? Don't you talk about renewable energies a lot? You know, things like we are fine with that. No, the news are very bad. So most of them are yellow, and 3 of them are red. That means because what they put in here is a tracking system. So if we think of having net zero in 2050, that's too far away. So what they put is like a milestone in 2030 by checking how are we now and how do we have to be to reach what we want in 2030 to arrive to 2050. So here, for example, I put you the one for carbon capture, utilization, and storage, which is one of the red ones. And you can see here is what is operating, under construction, and where we have to be in 2030. I should say, though, that this is changing rapidly. There are many companies and many countries that are actually implementing CCS, no utilization, CCS. But anyway, this is what we have. I say we have to have hope and we have work, correct? Okay, so this is coming from IRENA, the International Renewable Energy Agency. And here it defines 6 technological avenues for the energy transition. So that means that, number 1, there is no one technology that is the solution. That's impossible. So there are different technologies, and we need to combine all of them. And I'm sure you know them, but what I have here is the percentage. So what we have is that in order to reach net zero emissions, if we have the emissions we have today, then 25% will come from renewable energy. Only 25%. And it's a lot, but it's 25%. 25% will come from energy efficiency. That's what we usually do. We try to always increase the efficiency of the processes. That's normal for an engineer. So that's 25%. But if you remember in the previous one, we were doing very bad on energy efficiency. So we really have to work on improving that one. Then we have 25% from electrification. Electrification are beautiful Tesla cars in some places, etc. Electrification of industry, etc. 20%. Of course, then this electricity should come from clean sources, correct? And then we have 10% for hydrogen and 20% for CO2 capture, utilization, and storage. That will be either from fossil fuels or biomass. So then hydrogen and CCS have a very important role to play in this decarbonization. First, if we have natural resources, we can use them. So Brazil is rich in oil, to begin with, in oil, is rich in biomass as well. And here we have the wind map and the global solar map, in which we can see the places, for example, where I'm coming from, clearly rich in solar. So we have the cheapest solar energy of the world right now, okay? And then also wind, no much wind, but then there is wind in all these other places. So you are doing well in some of them, very well in some others. Brazil is a very large country. The reality is that the speed of renewable energies is increasing, not at the speed that is wished. Let's say it will now. I think with all this COP28, COP26, 728, it will. But I don't know also if you know, but most of the renewable energy that is put in place is hydro. It's not solar, it's hydro. And who is the leading country in the world in renewable energy? Do you know? The one that are putting more renewable energy in the world? China. Okay, so then renewable energy, then without renewable energy, electrification, blah, 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 blah. What good is the role of hydrogen? I mean, we talk, I don't know here in Brazil, but in Europe, hydrogen is like the golden gas. And then in the Middle East as well. So why do we talk a lot about hydrogen? We talk a lot about hydrogen because hydrogen is not an energy source. It's an energy vector. So you have to make hydrogen, but then it can be used to produce more energy. And this is why now we talk about hydrogen. By the way, I have been working on hydrogen for 25 years. And hydrogen goes up, down, now, down. Now it's very important, now it's not important, now it's very important, now it's not important. So there is a new paradigm for hydrogen because now hydrogen is combined with renewable energy. So you can use the excess of renewable energy to break the water molecule, convert that into hydrogen and oxygen, and then use the hydrogen to produce energy when you don't have renewable energy. So that's the main thing of that. But of course, now that you have it, you can also use it for other applications. We will talk about this later. So this slide is the slide that will cover the whole thing about hydrogen. First, have you heard about the colors of hydrogen? So hydrogen is a gas, no color, correct? But then you talk about gray, blue, green, turquoise, pink, rose, white, golden. So these colors come because of the molecule you use to produce the hydrogen and the source of energy you use to produce hydrogen. So green hydrogen, for example, is water and renewable energy. So if you use water, but you use the network, the grid, for producing hydrogen, and this is not renewable, that's not green, okay? Once you produce the hydrogen, then you have to utilize the hydrogen. This is a very interesting one. I say that the predictions, we never know what will happen, correct? So I took this one because depending on who writes the predictions, then you have different uses of hydrogen and different colors. IRENA, 12%, the International Energy Agency, 13%, and of course the Hydrogen Council, 22%. And also the colors, correct? I think it's on average like a 10%, correct? But then if you have cheap renewable energy, your hydrogen will be cheap. This is what is happening in the Middle East. So we are rich in oil and gas, but we are really rich in solar energy, in renewable energy. So for us, producing hydrogen is cheaper. Okay, I will use this data. I don't know if they have interest because I need to arrive to photocatalysis because you need to know photocatalysis. But let me use this data because, again, do you really speak about hydrogen in Brazil or not? You do. Okay, so here is data that is very interesting and is not used. So today, the amount of hydrogen that is utilized is here. Is 87 megatons of hydrogen. That's what is used today in the applications that is refinery, fertilizers, and chemicals. Okay, so if today we produce the same amount of hydrogen, but green hydrogen instead of gray hydrogen, the amount of electricity that is needed is 3,600 terawatts, which is the annual energy or the annual electricity used in Europe in 1 year. Imagine, for the hydrogen that is produced today, not for what is expected to produce. The amount of water is 670 million cubic meters. And that also is the amount of water, 1.3% of the amount of water that is used all globally for producing hydrogen from natural gas. Okay, so then we talk about the other thing that is also interesting, which is when we talk about CCUS, the U stands for utilization. If we produce 36 gigatons of CO2, it's impossible that we use it. What is used today in the market is 230 something. Okay. So what are the opportunities for CO2 utilization? Because we will need to capture CO2. Can we utilize more CO2? So we just published a perspective here in which we talk about the sources of CO2, and then we talk about either the concentrated sources of from air capture, then you can use enhanced oil recovery, and this is what we call CO2 conversion. So e-fuels for heavy transportation like trucks, trains, buses, or airplanes, or boats. And then we have chemicals, we have building materials. So this is the current market of CO2 utilization. This, okay, say 200 something is 300. Most of this is used for chemical products, essentially methanol. Then some of it is used for enhanced oil recovery, some of it for mineralization, and a little tiny bit for fuels. Where are we going? 20, 30, 7 years from now, I don't know. Maybe we have to see what happens in 7 years from now. So most of it will go to storage, as I mentioned, but then there is a huge opportunity for fuels, solid mineralization, biocharge, enhanced oil recovery, and chemical products. They are in scale within themselves, but not with the other ones, because I cannot put the 36,000 gigatons there, okay? But these are the opportunities. And then here are the technologies for CO2 conversion. Here on the top, we have the ones that are more advanced in TRLs from 5 to 9. Carbonation, thermochemical, electrochemical, that's the electrolysis. And here we have the ones that are lower in TRLs, and that's where we have photocatalysis. Again, I will explain later. So the people in the companies, how is this technology moved forward? Most of the applications are for producing e-methane, e-methanol, formates, and syngas. Again, all the details are in the paper that we just published. Okay, so where are we going? So this is where we are today. This is most of the energy that is produced today is from oil, coal, gas, methanol, and a bit of electricity. This is where we are going. Producing more energy, 1 more trillion, or 0.1 more trillion. And then most of it will be bioenergy, as Brazil has great opportunities for this. So bioenergy, hydrogen, methanol, and ammonia. This all come from hydrogen, actually. So it's almost 1/3. And then we have oil and gas and electricity. Okay. This is first part of my talk. Second part, briefly, I want to explain to you what we do in the RIT Center. Third part, photocatalysis. Okay? So these are some of the photos of the RIT Center. Actually, this is a photo reactor. This is the combustion chamber that I talked about before, Fred. And this is Carlos Luan. I don't know if you see him. This is an equipment that we have for CO2 capture with solvents. Okay, so this center I mentioned already, you don't need to read. I already explained to you what the RIT Center is. It's the first center in the region in which we combine CO2 and hydrogen, and one of the few or the first ones in the world doing this. So I already mentioned that we have 5 different themes. So what we do is, because we are many people in the center, so we have different themes with one lead, and then professors, students, postdocs, etc. So here is the team. Okay. Again, what we try to do is, not everyone has to be an expert on everything. What we try is to bring complementary expertise. And that's what we have in the center. So don't think I know everything I'm going to tell you today. I'm trying to learn from them. But my area of expertise is my area of expertise, okay? So we do have different labs that I invite you to visit, and then we also have core labs and many collaborators. So what do we do on CO2, in case you are interested on CO2? So we work on solvents, adsorbents for CO2 capture to overcome the limitations of the current ones, and we work on the processes as well. Then on CO2 utilization, we work on different aspects. E-fuel, using the CO2 to convert waste into materials, etc. And then one of our areas of expertise is that we do multi-scale modeling. So from quantum chemistry to process design, techno-economical assessment, etc. As an example, I'm going to give you the one that you have on the top. These are seeds from dates, Tamer. And this is, we have produced activated carbons. We have used them in the lab, and we have modeled this process, and we use now these date seeds to capture the CO2. Okay? Then on hydrogen, we do something very similar. We work on clean technologies for hydrogen production. We actually work on the ones that are clean, as I said before. We work on what is called power to X, any application of hydrogen. We do multi-scale modeling, and then we are very fortunate because we are actually associated to the Masdar solar platform for technologies. On sustainable fuels, we use the CO2 we capture in theme 1, we use the hydrogen we produce in theme 3, and then we produce synthetic fuels, but we also use waste from agriculture, from any place to try to produce this bioethanol or synthetic fuels for aviation or any other fuels. Again, we do multi-scale modeling, and we use the facilities in the solar platform. So for the slide that I showed you before, we cover all of them with one theme or another. I'm not going to talk about this, but I'm going to tell you that one of the projects we are doing, for example, is in the production of biofuels. What we do in this case is we design the catalyst to improve the efficiency. Okay? We are also working with Sir André Geim, the Nobel Prize, who discovered graphene, on using graphene and other 2D materials for hydrogen, for the hydrogen economy, for fuel cells, and for electrolyzers as well. And then we use solar green hydrogen production from water and H2S. Okay, third part of my talk. Are you all ready? Okay. So now, first, do you know what is electrocatalysis, correct? Okay, so you know that when they talk about producing hydrogen from water, it's water splitting with an electrolyzer. And that's the most advanced technology, still expensive and need to be improved. Okay, that's electrocatalysis. So I use electricity, and from the electricity I break the molecule and convert that into oxygen and hydrogen for the case of water. Okay, photocatalysis is also a catalytic reaction, but instead of using electricity, you use directly the light. Okay, so for electrolysis, you need to have a lot of energy coming from the electricity. This will be the light directly. So when people say that the sun is free, the solar energy is free, no, you heard that, no? Okay, so then why don't we use it? But in this case, it could be if we have the right photocatalyst and we improve the efficiency. That's photocatalysis. So they are similar in which they produce similar chemical reactions. However, the photocatalysis has light versus electricity for the case of electrocatalysis. The type of reactions are different, the type of applications are different, and the type of materials are different. For photocatalysis, you need to have semiconductors. For electrocatalysis, you need to have metals or metal oxides, and that's one of the problems of electrocatalysis. You need to have platinum and all these precious metals, correct? Okay, now there is a lot of words here, but I will explain briefly. So here we have what are the benefits of using photocatalysis. Essentially, because of the type of light you use, it's environmentally friendly. Actually, it's used not only for hydrogen production, it's also for water treatment, for removal of contaminants, for example. It's very efficient energetically, it's very versatile. Once you have it operating, the cost is very cheap, and also you don't need chemicals. So with the environment, it's very nice. Electrocatalysis, as I mentioned, the TRLs are much higher because it's scalable. That's the last comment I put there. It's much more efficient today, and then it's also tunable. You can work on many different things for that. Okay, but we decided to work on photocatalysis. Why? Because the main limitation of photocatalysis is that the photocatalysts are not efficient, very little efficiency. So if you improve the efficiency of the photocatalysis, then the whole thing is much better because the type of equipment you need are much simpler because of the conditions. You don't have corrosion problems you have with electrolysis. You can have many benefits. And that's where science comes into place, correct? Maybe a company say this is too far away, but for us as scientists, improving this, it has a huge impact. It can have a huge impact. So these are the technologies we are working on right now. So first is the water splitting. Then we have H2S splitting, CO2 reduction. Here is, in one word, what is photocatalysis. What you have is a material, a semiconductor, in which this is activated. Oh. This is sorry. This is activated by light. So then the electron from the conduction band will go to the other band, and then you can produce from H2S, you will produce sulfur and hydrogen. From CO2, you can produce synthetic fuels, because usually it goes with hydrogen. From water, you have hydrogen and oxygen. So essentially, the solar energy will activate this reaction in the semiconductor. They have to be stable, they have to be low cost, and they are environmentally friendly. So that's photocatalysis. And then I say we work on H2S. Do you know H2S? It's nasty, no? From the odor to safety, many problems, correct? So this is actually corrosive, toxic, not like water. Water, nice, friendly, environmental. No, this is the opposite. But it's actually harmful. It's horrible, actually. But then there is a variety of industrial processes in which you have H2S. And you need to handle it. And the most known case, at least for us in the UAE, is to remove it from natural gas, correct? Otherwise, you cannot sell natural gas. So usually, actually, thermodynamically, it's much easier to break H2S than to break water. So thermodynamically, it's easier. And then today, this is used by the Clausius process to remove it from the system and then to produce sulfur, and then usually you produce water. But then why do you produce water if you can produce hydrogen? So that's why we are now working on hydrogen. This is the approach we are following. So we do experimental work. We have in our lab a photocatalysis lab in which we do the experimental work. So we design the photocatalyst, then we have the reactors, then this photocatalysis that I mentioned. Here are some of the materials that we use. Then we use computational modeling, density functional theory combined with other modeling approaches. And then we do machine learning. I will explain to you right now. And then with this, we do data-driven science, accelerate development for this. Essentially, the applications that I mentioned, hydrogen production and CO2 reduction. We published a paper review paper on how this can be done. And then I already explained to you, so here we have the valence bond in which we have an electron that goes up to the conduction band, and that's how you need to have the right band gap to have a good photocatalyst, okay? So this is the range of the energies that you need to have. And of course, the light source has to interact with the semiconductor material, so your photoreactor should be transparent to light. It's obvious, correct? But it's needed. Okay, so then what are the most common photocatalysts? In 1D, carbon nanotubes, metal nanorods. These are good materials because they have a lot of surface. In 2D materials, graphene and two other materials, MOFs, that they have good current transport. And the 3Ds that we have can be metal oxides that they have good volumes for the transmission. But this is not only that you have a geometry. You need to have into consideration the composition, the stability, the cost, many other things, okay? And that's why you need to do modeling. So this is a plot that I'm sure you have seen many times because you do process modeling. So let's use it again. Here we have the time scale. Here we have the length scale. And then we use DFT. That's how we start. So we work in this area. Quantum mechanics, molecular dynamics, including reactive force field and kinetic Monte Carlo. And then we use machine learning to speed up which one are the best ones that then we put in the process simulation and in the engineering design. And anytime we do modeling, we have to do experimental work. So we use our experimental work and the experimental work of others to speed this up. What is density functional theory? How many of you know density functional theory? Few. All of you. Okay. Then I don't need to explain. Okay. So density functional theory is a computational quantum method that is based on the electronic structure of the atoms. And then from there, you can obtain many properties. In addition to the density functional theory, which is to solve a problem with DFT with some approximations in the Schrödinger equation, we also need to have the crystallographic information of the catalyst. And then we have a software. So for this, usually we use BASP. I don't know, do you have it? This is a license. You have to pay a little bit of money. It's not very expensive. But you can also use Quantum Espresso, which is free, for example. Okay, so here you have in the software, then you have the functionals. You need to have all the interactions. You need to take into account all this to model that. And then in BASP, for example, we have the explanations. These are the details that we use from BUS to model these systems. First, we have to build the lattice from a database. Then we optimize this with DFT, and then we calculate the relevant properties. So the band gap, this gap that we have between the two bands that we need to have the electrons moving from one to the other, absorption behavior, the reaction pathways, and the energy analysis. Machine learning. How many of you are using machine learning? 1, 2, 3, 4, 5. Okay. So machine learning is everywhere now. It's used for everything. But we have to be very, very careful the way we use machine learning, because in fact it's a brute force method. So unless you supervise yourself what you are doing and what is coming, you can get, if you enter BS, you get BS, correct? Okay, so there are different algorithms that you can use for machine learning. You can use a supervised algorithm, unsupervised algorithm, or reinforcement algorithm. A supervised algorithm is you have to take care of what you are entering, and then you will see a correlation with what is coming. And then for this, we have artificial neural networks in which you have several layers. This is your input layer, the ones, the descriptors you are putting. This is the output layer, the information you are getting. And in the middle, you can have one or several hidden layers. So essentially, in this, we have input data. We have that we use for training, because like humans, the machines need to be trained to learn. So you use a set of data for training your algorithm. Then you have a set of data for testing how well they have learned, like the exams that Fred has here. See how the students have learned what you are teaching. That's actually what you do for machine learning. So how my algorithm understood what I wanted and got it. And then depending on what you get, you may have to refine that. So for example, this is the one that we use, the supervised algorithms. And then you have many other algorithms, random forests, artificial neural network, Gaussian processes, many of them. Okay, so I don't think I will talk about all the examples. I will give you 2 examples, okay? But if you want more, we can talk later or another day. Actually, all of them are in the publications, except for one that is going to a journal that is not ready yet. But so these are some of the examples of the work we have done. This is actually the PhD thesis of Yutin Lee. She is now a postdoc in the group, but working on the project with the Nobel Prize. So another project. And then Daniel Bahamon, I don't know if you know him. He's a senior research scientist from Colombia. So we are also very international. Yutin is from China. Daniel is from Colombia. And here are the insights into the mechanism of H2S absorption. Then we get a paper in Nature Computational Materials on a screening procedure on how to find these materials. And then we have done this for another application, photocatalytic CO2 reduction, and then also using a liquid, supercritical CO2, liquid, compressed CO2 instead of a gas. Okay, so this is the first work. First, in our review, we found that CDS, cadmium sulfide, is the most used catalyst experimentally, and no one had studied it theoretically. So we went there, we found that it has the right band gap, and then we calculated the absorption, dissociation, and everything. We found the most stable surface, which is 110, and then we also discovered that when you use only CDS, it gets poison. You have sulfur on the surface, and that's it. That's the end of your catalyst. So you need to do something else with this. And then another interesting thing we discovered is that when we generate a vacant, which is a way to improve the performance of these semiconductors, then the efficiency increases greatly. You calculate these energy profiles, which are called reaction coordinates, and if you have lower energy, it means this is more stable, better. Okay? So with this, we say, okay, we have learned this. What do we do next? What we did next is, okay, what is done experimentally again? What they have discovered experimentally is that when you do a co-catalyst doping CDS, then the amount of hydrogen that is produced increases. This is doping with one metal or doping with 2. So then we went to our modeling approach and we say, okay, let's explore hundreds of materials by doping different ones. So this is what we did. This is the one that went to Nature Computational Materials. So we pick out transition metals from 3D, 4D, and 5D series in the periodic table. We first studied the stability, then we calculated the band gap and the band center, and then finally we calculated the activity, and with this we found single transition dop and double transition dop for CDS. I'm not going to go into the details of this. I'm going to explain only how this is performed. So first we calculated the stability. By calculating the energy, we killed already some of the metals, transition metals that we were using. Then we also calculated the band gap. I told you that we need to have the right band age. Then we calculated the band gap center, and with this we also discovered the good ones and the bad ones of the movies. And then we calculated the absorption energy, and they need to be in this quarter, so these ones are also out. Essentially, the procedure that I explained before. First, the surface should be active, then they should have the right energy, right band gap, right energy for reactions. And with this, the last one is that we did is we calculated the free energy of absorption. It should be close to 0. So we came with materials. Some of them have been tested experimentally. Some of them appear here for the first time. And that's why it went to this journal. For example, the one doped with cobalt was an explorer. Then we also studied the combinations of both of them. You can find this in the paper. And we have used the same approach, exactly the same, for another problem. Now it's for calculating, for doping a photocatalyst for CO2 reduction instead of for hydrogen production. This is the beauty of science. We can use our knowledge and apply this to different problems. So we use the same procedure. Of course, we had to do all the calculations. We need to understand the physics of the problem, etc. But we could do this for these other materials. This is a collaboration we did with Nuria Lopez in ISIC in Tarragona. So one of my PhD students, Yutin, went there as part of their, her PhD work. That's something we can also explore here. We published this paper very recently in the Journal of CO2 Utilization. So we did something similar. There was one dopant that was cobalt that was good for this reaction. So we got the periodic table. Can we use other transition metals? The procedure was exactly the same, so I don't need to explain that. And we did exactly the same, and we came with other dopants that could be good for this reaction, okay? Which is what you have here. Okay, and 2 of them were validated experimentally, and 1 of them is new. So what I'm explaining here, and I think I'm going to stop here so that you have time for questions. What I'm explaining here is that you can use computational modeling. First, you need to understand the experiments. You need to find where the issues are. Then you can use computational modeling to understand essentially the beginning, and then you can combine this with fast screening using other tools and come up with materials that were not used experimentally but will be much better than the one you have experimentally. Then you prove that, and then you can do your process design, you can do your techno-economical assessment, and you can have the best or an improved material or a new process for the application you are looking for, okay? So with this, I'm not going to explain the other 2. I have beautiful results, by the way. But no, because I want to go to my conclusions. Machine learning, I will send you the paper. This is what we are doing now from the whole 800 possible materials. Okay, so the take-home messages. CCUS and hydrogen, that's how I started my talk, is not the solution, but it's part of the solution. And of course, this is huge, so we have to work on specific areas trying to improve them. And that's why there are many PhD theses available, many projects, and many possibilities for collaboration. Fundamental science is important, very important, to move this forward to industry. But we also need to know what are the needs. That's why we have to do cost analysis. We can find the most beautiful material that can stay in a beautiful lab for nothing more. And that's nice. It can even has a paper in Science or in Nature, but it's better if you are able also to move this forward. And I think we need to think about this from the very beginning, correct? Because we need to, this low-cost thing is important, that we have to consider that there are precious metals that are very limited, for example. And then also very important is that we cannot work isolated. We have to work with other people, talk to other scientists, go to seminars on topics we don't know, go to talks in a conference on topics we are not working on, because that's where you can get new ideas for new things that you can merge with what you have, okay? So be brave and don't be scared of doing new things. And I want to end with something that I think is important. The future is here. What did you see there? Water? Okay. So water will be one day employed as a fuel that hydrogen and oxygen, which constitute it, used singly or together, will furnish an inexhaustible source of heat and light intensity of which cold is not capable. And this is from the mysterious island, Jules Verne, 1974. So I said the future is here. Do you know what happened? Why this didn't happen? You don't know. So at the same time as this was written, we discovered oil and we invented the combustion engines. And that's it. So that was cheaper, faster, etc. Now we are back to this. So the future is here, as I say. So thank you very much to Fred, to all of you for your attention. Muito obrigada. And thank you to my team. You see, this is very international. I have 12 people from 12 countries. Okay, so that's really, truly international. And on the right, you have some of beautiful photos of Abu Dhabi, including the one on the top. That's the mangroves, Fred. So you have water, you have mosque, you have everything. Thank you very much.